Thanks, and thanks a lot for the organizers for the invitation to give a talk at this nice workshop. And well, I'm sorry that I cannot be there in person. I was actually checking the flights from South Korea, but it turned out to be extremely complicated to get to Italy at this time. But anyways, so I will talk about neutron star mergers and not about domain walls. So sorry about that. And the main reason is because Romuald Janovic just gave a talk about the domain walls in this related Simon's seminar series. So if you want to hear about domain walls, you should check the very nice talk of Romuald, which you can find on the webpage of the Simons Center. But anyways, I will go to the neutron star merger. So the outline of the talk is like this. I will start with a brief introduction and motivation to the topic, and then I will introduce this QCD model and discuss dense quark matter and dense nuclear matter, how they are implemented in the model. And then I will tell you about these hybrid equations of state, so what they are and how they are used to model QCD at finite temperature and density. And then last is probably the most important part is where I talk about the application of this model to neutron star mergers, in particular discuss the production of quark matter. But anyways, I will start by introduction. And the first is the QCD phase diagram. I think we have seen already different versions of this phase diagram in this talk. So this is one part possible guess. And in this talk, the focus will be on the matter at high density, where you have the region of dense nuclear matter, which is dense liquid of protons and neutrons, with extremely closely packed, and then also the quark matter phase, which is an even denser phase of free quarks and gluons. And as you can see, there are lots of question marks here in the phase diagram. In particular, it's not known what is the nature of the phase transition between nuclear matter and quark matter, or even if it exists and the critical point. And this is, well, one of the reasons is that it's very difficult to test this phase diagram in the laboratory, and this is mostly due to the very high characteristic temperature scale of QCD, which is difficult to reach in laboratories. But there is lots of effort to study this in the heavy ion collisions, well, which mostly take you to this like not so dense region, but like more recent experiments at RIC and future experiments at FAIR and NICA and other places will try to push this knowledge to higher densities, but it's still difficult to reach the region, which is like the focus of this talk. But I'm actually, well, the other reason why there is question mark in this region is that also the theoretical knowledge of this at intermediate densities is not so great. And that's what I will then discuss next. So I will sketch what is known about or which regions of the phase diagrams can be covered by different theoretical or computational methods. And well, maybe one of the most important methods is lattice QCD, but due to the sign problem, lattice data is only available at 0 or relatively small chemical potentials. And then there is lots of different methods to discuss the theory at low densities and low temperatures, like nuclear theory and different kind of which all in some sense use effective description of the theory in terms of hadronic degrees of freedom. And then there is also knowledge from perturbative QCD at, I think, well, very high temperatures and chemical potentials. But these methods leave lots of questions at intermediate densities. And this is not only of academic interest, this region, because, well, we know that the neutron star core densities lie in this range, possibly probing even the phase transition. And on the other hand, if you look at neutron star mergers, then you get matter which is heated up, so it covers this light violet region roughly. So what does this mean? This means that, well, improving theoretical predictions is important so that we can access this white region. And also this means that there will be incoming experimental data from neutron star measurements, by both measurements of isolated neutron stars and neutron star mergers. And the one thing is that this white region is a region where the dynamics is generally strongly coupled. So maybe you can use gauge gravity duality to model this region. But let me first comment on a little bit on the neutron stars. So from the point of view of the phase diagrams, well, neutron stars can be seen that they are just blobs of extremely dense cold QCD matter. Well, they are actually quite hot in terms of kelvins, but with respect to QCD scale, their temperatures are low. And what you can do is that you can use this Tolman-Oppenheimer-Volkoff equations, which is the high general relativity analog of hydrostatic equilibrium, to map the equation of states of QCD to mass radius relation of neutron stars. So what this means in particular that by this mapping, the equation of state of QCD can be constrained by measuring masses and radii of neutron stars. And there is already lots of measurements available. There is more information on the masses of the neutron stars. There is already dozens of results using various methods. I'm showing here a slightly outdated summary from Jim Latimer on the right. And the most important of these measurements are some of these points here, which are these Shapiro delay measurements of neutron star white dwarf binaries. And some of these masses are extremely high, and they set a strict lower bound to the maximum mass of the neutron star, because there is a theoretical maximum mass of the neutron star, but it needs to be at least so high that you can explain these observed neutron stars. And then there are also radius measurements, which are more challenging and have higher uncertainties. Well, in particular, there you can model cooling after X-ray bursts and observe the X-rays. And after some modeling, you can estimate the radius, and typically you get radii which are around 10 to 15 kilometers. Some experiments claim even better uncertainties. And what is important is that more and better results are expected to come in near future. For example, the NICER experiment, which measures very precisely rotating signals from related to rotations of neutron stars. But the other thing which came up already was the use of gauge gravity duality. So is it, well, of course, many people have thought that maybe it's a good idea to model dense QCD by using holography. There is like already since 15 years, so there are some studies in the literature of putting some sort of dense matter in various gauge gravity duality models like D3, D7 models or Witten Sakai-Suki model. And I won't be talk about anything about the details. I mention here some of the references. But more recently, there have been several studies which really try to focus on neutron star physics and get more precise predictions for neutron stars. Well, there are some studies of using D3, D7 for quark matter, something else for nuclear matter, and studying possibility of exotic phases in QCD, and some studies using Witten Sakai-Sugimoto model, which also include some nuclear matter in some approximation, and also some studies in bottom-up models like Einstein-Maxwell dilaton. I mean, if you don't know what these phrases mean precisely, this won't be important for the rest of the talk. But what I will be talking about today, and what was actually already covered by the talk of Ed van Geel on Monday into great detail, is that there are various studies using the VQCD model. This will be the topic of this talk. And that brings me to the second part of the talk, where I discuss VQCD and how it's used to model a dense QCD matter. And first of all, I will discuss a little bit in detail or some model details of this VQCD model, and in particular how you model quark matter in this model. So this is a holographic bottom-up model for QCD and the Veneziano limit. So a Veneziano limit means that, in principle, you start by taking the number of flavors and number of colors of QCD to be large with NF over NC fixed. And this is actually where this V in this abbreviation arises from. It stands for Veneziano. And this is a bottom-up model. I mean, there is a string theory motivation coming from a 5-dimensional non-critical string theory, but at some point you will need to switch to switch to a bottom-up approach, where you no longer try to derive it directly from string theory. And in a little bit more detail, the model is obtained by fusing together two building blocks, which have been studied a lot in the literature. And the first building block is this IHQCD, stands for Improved Holographic QCD, which is a model for pure clue inspired by string theory. It's based on a 5-dimensional Einstein dilaton gravity. And then the second framework which I'm using is how you add flavor and chiral symmetry breaking in these kind of models. This is done by adding space-filling D4 anti-D4 branes in and a Sen-like tachyon condensation. These are imposed by this brane setup. And in terms of actions, the action of the model, if you're just considering quark matter, looks like this. So the main degrees of freedom are the two bulk scalars. This lambda, which is dual to the trace F squared operator, and we denote it by lambda because, well, near the boundary, it becomes the source of this operator, which on the field theory side is the 12th coupling. And the other scalar field is this tau, which we call the tachyon, and it's dual to the QQ bar operator in QCD, so it will control, or it controls chiral symmetry breaking. And so the action here, well, this is everything that you need to describe quark matter. So it contains two terms. The first is the improved holographic QCD action. So this is Einstein gravity, and then you have kinetic term and so far arbitrary potential for the dilaton field. And then the other building block is what comes from this flavor sector. So this is a generalized action for this pair of D4 anti-D4 branes, including the tachyonic potential. But well, the important thing here is that because we are working in the Veneziano limit, you really cannot derive this brane action strictly from string theory. And then in order to parameterize our ignorance, we have included these arbitrary potentials, which would be some known power laws of lambda for like DPI action in string theory. So we have switched to a bottom-up approach. And this means that this is an effective model. So you have many potentials, and it will be essential to fix these potentials by comparing the QCD data so that you can then make predictions for QCD-like theories. And in order, perhaps the most important comparison which you can do is that you compare to lattice data to thermodynamics at finite temperature, which I'm doing here. So actually, well, many parameters of these potentials are already fixed, but before doing this fit by requiring qualitative agreement with QCD. But it turns out that, well, you get for this fit, which I call that it's stiff, which means that you have really many parameters in principle, but the results are not really sensitive to them. So the result is first and foremost prediction of gauge gravity duality. So changing the parameters is like really fine tuning. And that's why it's like really non-trivial that you can describe the lattice data very well. So I should tell you what precisely we are fitting here. So the first plot is the interaction measure for 2+1 flavors. So the red dots is some relatively old Wuppertal Budapest lattice data for the interaction measure as a function of the temperature. And these blue curves are different fits by using the VQCD model. So there is actually some leftover parameter freedom, which is not fixed by the lattice data. And then there is this baryon number susceptibility. So the first non-trivial cumulant of the pressure at zero chemical potential. And here also we can get a very nice fit to the lattice data. And okay, when after the model has been fit to lattice data at small chemical potential, then you can ask, how does it work at larger chemical potentials? And here I'm doing sort of this extrapolation of the lattice data to a sort of extreme limit where I take the temperature to be exactly zero. And so I'm just considering the equation of state for cold quark matter. So the result is shown here. So the log of the pressure versus the log of the energy density. And these green and blue curves are the results for quark matter from the holographic model. And they compare nicely to known constraints. And I think what you should check in particular here is the gray band. And this gray band gives you all polytropic interpolations between known perturbative QCD constraints and at high density and nuclear theory constraints at low density. So at high densities where you are in the quark matter phase, your curves really should be in this band, and we are pretty much in the middle. At low densities, we deviate from the band, but this is not a problem because at low densities, you expect that you will go to a nuclear matter phase. And actually, I'm comparing here also to some well-known nuclear matter equation of state, which are these colorful curves. And well, I should mention that this extrapolation idea is sort of not new. This kind of thing has been done in the literature in the context of studies of the QCD critical point, but here we are sort of pushing it to like even higher densities and looking at the quark matter equation of state. But okay, so far this model was only for quark matter, and we also need to add nuclear matter. And this was already discussed in great detail by Edvan on Monday. So you need to look at the solitonic instanton configurations for gauge fields, which gives you the description of nucleons and baryonic matter. And this has been studied a lot in the literature in the context of Witten-Sakai-Tsukimoto model. People have been looking at the matter at finite density, and well, there are different things. I mean, in particular, the baryonic phase has these soliton crystals with non-trivial transitions. And well, soliton solutions have also been constructed in hard-walled models and in VQCD. There is work in progress, which Edvan was talking about. But in this model, actually, I won't be doing anything about the solitons or instantons because maybe you learned from Edvan's talks that these instanton solutions are very hard. So instead, we are trying to do something simpler. We just set NF equals 2 and tried a simple approximation scheme where we just consider homogeneous nuclear matter. So the idea is that maybe this is reasonable at high densities where the nucleons are expected to essentially overlap. And it turns out that the ansatz that you should use is this kind of where the non-abelian gauge field, the spatial component is locked to the index of the 2x2 Pauli matrices. And well, but I won't go to any details on this. I will just show you the main results that you get. So the phase diagram from the model just by computed just by following the dictionary looks like this. There are, well, even in the absence of nuclear matter, there are these two phases, like this phase and this phase. So the low temperature confining phase is a geometry without a horizon, and the like high temperature, high density deconfined phase is obtained as a black hole in the holographic model. And interestingly, then when you turn on the nuclear matter or consider also configurations which have a nuclear matter, you obtain an additional phase, which is that this is the nuclear matter phase appearing pretty much where you expect it to. expected to occur. And then you can also look at the equation of state. Again, also now for the nuclear matter here at low temperature. And what I'm plotting in this plot is actually the speed of sound. And you observe that here in this range, which is the nuclear matter range, the speed of sound exceeds this 1/3, or speed of sound squared exceeds this 1/3 value of the conformal theories. So which means that you get very high values for the speed of sound, which means that this means that the equation of state, you call it that it's stiff. And this is important because, as it turns out, this helps to pass the bounds from neutron star observations later when I really use this in apply this for neutron stars. But okay, this was everything I wanted to say about the holographic model itself. And now I will do more applications and tell you what are these hybrid equation of states. Namely, well, if the model was ideal, we could directly use the equation of state from the model in neutron stars and neutron star mergers, but this is not the case. The model equation of state is not good enough to really be used in state-of-the-art simulations. And we want to create something which is good enough. And the most important issues is that this homogeneous approach for nuclear matter that we are using, it only works at high densities. So at low densities, the predictions are not reliable. And then there is another issue, which is actually a large NC issue, is that the temperature dependence is trivial in the confined phases, which also includes the holographic nuclear matter phase. So there is no temperature dependence. And the temperature dependence would be a like loop effect in string theory, and it's very hard to analyze. And so how do we solve this? Well, we say that at low densities, we just abandon holography and use traditional nuclear theory results because we already know what the equation of state should be at low densities. So we just take our favorite model from the market and use that. And for the temperature dependence, this is a bit more tricky because there is really no reliable model to use for the temperature dependence available at the moment, in particular for densest nuclear matter. So what we do is that we just borrow the temperature dependence from basically the simplest reasonable model that we could think of. And so what we pick is this van der Waals gas of protons, neutrons, and electrons. So just like ideal gas plus excluded volume effects for the nucleons, which actually you need to also add some mild interaction potential. And with these solutions, or well, in a little bit more detail, what we construct then looks like this. So this is here on the right is the sketch of the constructions. So we use VQCD for the quark matter phase and also cold and dense nuclear matter. So here, and in order to get the temperature dependence in the nuclear matter phase, we use this van der Waals construction, which is the construction is done in such a way that it agrees exactly with the VQCD prediction at 0 temperature. So it gives an extrapolation of the VQCD result to higher temperatures. And at low density, we just put in this DD2, Hempel-Staffner-Pili DD2 model. This is very like popular model in the context of neutron star physics. That's why we want to use it. But actually, as it turns out, only using this DD2 model would give you a very stiff equation of state, so very high speed of sounds, which would be in slight tension with observations. So that's why we also put a little bit of APR equation of state here in the middle. And as it turns out, this HSDD2 equation of state doesn't have any meson gas contribution, which is important at low densities and high temperatures. And even though we are not really focusing in this region, we just plug in the meson gas contribution in a very simple approximation. We just take the mesons from PDG and add the pressure of free mesons. And this is already enough for our purposes. This is enough to look at or study the location of the critical point, because as it turns out, this construction will give you a description of a critical point. But okay, let me discuss in a little bit more detail the results, starting from just the result for the cold equation of state. So from this construction, we pick 3 different models, which we call the soft, intermediate, and stiff models. And these choices reflect the degrees of freedom in the VQCD model, which is left free by the fit to the lattice state. And here, well, I show the equation of state. So again, the log of the pressure against the log of the energy density. And from these labels, you see from which source the equation of state is coming from each region. So we start at low density with nuclear theory, so no holography, but the rest is all coming from the holographic model. So you have the region with holographic nuclear matter, then there is a phase transition, and then there's a region with holographic bulk matter. And these 3 curves give you the equation of state for the 3 different models. And it's important to compare them this to predictions, and well, the models agree with predictions with nuclear theory and perturbative QCD by construction. And if you look at the band spanned by all possible equation of state that interpolate between these 2, our models lie somewhere well within this band, as they should be, because they agree with the observations. And this red band is actually what you obtain if you include not only these 3 models, but all possible models using VQCD, or reasonable and also a little bit unreasonable models with VQCD combined with other models. So this kind of construction would span all of this red band. So you see that there is actually a non-trivial constraint coming from the model with respect to these polytropic constructions. And then what you can also do is that you can take this equation of state and plug them into the TOV equation, which gives you the structure of the neutron stars, and in particular this mass radius curves of neutron stars. So these solid curves here are the stable branches of neutron stars in the 3 different models. And these colorful regions here are constraints from measurements of masses and radii of neutron stars. And our predictions compare well with all these observations. And then I can go to look and check how this equation of state changes when you go from 0 temperature to finite temperature. So here you see that, well, there's this phase transition, which is here at 0 temperature. And when you go to finite temperature, it gets to lower pressure and gets actually weaker, and then it disappears altogether when you go to very high temperatures. And this band here reflects the variation of the model when you go from soft to intermediate and stiff models. And this change in the phase transition can also be seen from the phase diagram, which I saw here. This is as a function of the temperature and baryon number density in units of the nuclear saturation density. So we see that indeed there is, there's a first order phase transition, which is here as a function of the number density. You also obtain a mixed phase, and the first phase transition ends in an approximate critical point here. And these curves which I'm showing here are the colors indicate the speed of sound. So you see that for dense nuclear matter, the speed of sound is high. As I mentioned earlier, it even goes up to something like 0.55 for the stiff model. And on the right here, I'm showing the latent heat at the phase transition. And it's actually very high. it's a strongly first order phase transition. And you see that the latent heat at some point, well, it decreases with increase in temperature, and at some point it goes to zero, and this indicates the location of the critical point, which in our model lies between 110 and 130 MeV. But okay, I still have one topic to cover, and this is the holographic neutron star mergers. And let me first say, yes?
That you have 10 minutes.
Okay, so let me first say a couple of words about neutron star mergers without holography. Well, they are significant sources of gravitational radiations, and then, well, when you have these complicated merger dynamics, properties of dense matter are encoded in the gravitational wave and electromagnetic signal arising from these events. And here I'm showing schematically what can happen in these mergers. So as a function of the time and the mass of the binary. And this on the right, these are the possible gravitational wave signal that can be emitted. So for very massive binary, you get a merger and it immediately collapses into a black hole. But if you have slightly lower masses, you first get a hypermassive neutron star, which is some differentially rotating object, and when the differential rotation stops, it collapses into a black hole, and this happens in a rather short time scale. But for lower masses, you get a differentially rotating neutron star, but at some point the differential rotation stops, and the remnant is a neutron star, which may still collapse into a black hole at a longer time scale, for example, after cooling or something. And well, there is already one good event of this gravitational waves from neutron star observed. It's this GW 170817. And also a few other events have been observed. And well, what we want to do is that we simulate this binary neutron star merger by using our equation of state. So we have to solve the 3+1 dimensional general relativistic hydro equations with some good initial conditions for the binary neutron star. And we use our equation of state as input. And we use this also for initial data. We use this spectral code Frankfurt University Gara, in short FUCA. And for the binary evolution, so the GR hydro evolution, we use this Frankfurt in Illinois code, which is implemented in the Einstein toolkit. And this is heavy computing, so there is a project on the Hawk supercomputer. So we have a project on the Hawk supercomputer at the High Performance Computing Center Stuttgart. And I think now it's time for the mandatory movie, which I somehow cannot. Maybe I can do it now. Okay, but maybe before I show you the animation, I should explain what is shown here. So these two plots here are the the density distribution on the top and temperature distribution on the bottom. And this plot is on the equatorial plane of the binary, and this other plot is on a plane which is perpendicular to the plane of rotation. And on the bottom, so the bottom you will see the gravitational wave signal arising from this main merger. And this is actually for the soft equation of state. And well, we are using parameters obtained from the GW 1708-17 event, but with mass ratio. The mass ratio is not fixed by the observation of the inspirer from this event. And for this particular simulation, we chose a mass ratio between the constituent, which is 0.7. So, well, what do we see here? Well, this is the inspiral phase, and at some point, the neutron star will merge, and you see that because the mass ratio is different from one, the merger event is asymmetric, and well, and this is, and for the soft equations of state, you actually observe a collapse into a black hole, so that the gravitational wave signal is cut off and the neutron star remnant disappears after a while. But okay, let me then, okay, I don't, oops. Yeah, let me then discuss in a little bit more detail what we observe in these simulations. And the most important feature that we observe is the production of quark matter. And what I'm showing here on the top, top row is well, I'm showing snapshots from the exact same simulation that you just saw. On the top row, this is the number density. Then here I have the temperature. And on the bottom row, this is the fraction of the quark matter phase, or fraction of quark matter in the simulation. And these three simulations, snapshots here are at different times in the simulation. At very early times, we see this formation of quark matter, which we call the hot quark matter. And this is because the formation of quark matter here correlates with the hottest parts in the simulation, as you can see from here, because the contours of, well, these contours indicate where the quark matter was created. And then at this medium, intermediate time snapshot, you also create a little bit of quark matter, which we call warm quark matter, and this is no longer correlated with the temperature, and it's actually also not in the center of the remnant. And at late times, then you create essentially a quark matter core, which is a cold, so temperature is low, and it's right in the middle of the remnant. And okay, I have here in a little bit more detail on where the quark matter is produced, because I'm a little bit short of time. I will skip this left-hand plot which shows where the quark matter is produced on the phase diagram. But instead, on the right-hand side, well, here you also see what is the location of the quark matter as a function of temperature and the baryon number density, or this diagram shows the amount of quark matter which is produced. And this snapshot is actually the same time where you saw this, where I saw this production of hot quark matter on the previous slide. Or actually, all these snapshot times are the same as in the previous slide. So this first plot shows the production of hot quarks at this time. This is representative for the production of warm quarks, whereas this last plot shows the production of cold quarks, which is highest here at very high densities and low temperatures. And we have also analyzed, so this is for the same simulation as earlier, so a soft model, but we have also analyzed the intermediate and stiff models, and which lead to significantly suppressed quark formation. And then we have also studied the gravitational waves from these events. And these are all from the soft simulations, but then here we compare the simulation results. Well, this is for equal mass binaries, and this is equal mass binaries, but excluding the quark matter phase from the equation of state. So we see that the most significant feature of this phase transition is that it induces the collapse into a black hole for the soft equation of state. And this actually implies, this is in slight tension with the electromagnetic signal from GW170817, which implies a new constraint for the equation of state. So the soft model is essentially excluded.
Yeah. Very good. I think we have to start discussion, right?
Yeah. So I'm finished. I'm just leaving the conclusions here.